Hello everyone, my name is Kunal Goyal and I am presenting my PowerPoint presentation on learning-based battery control for cost saving and privacy preservation for smart meters. I would like to acknowledge the authors of the paper. The paper is published in 2017 47th Annual IEEE International Conference on Dependable Systems and Networks. The paper was added to IEEE Explore on 31st August 2017 and the link for the paper is given in the presentation. A brief overview of the topics that I will be covering in the presentation. Firstly, we will be discussing briefly about the system mode, key design objectives, and then we will talk about reinforcement learning and Q-learning and the algorithm. After that, we'll discuss about the metrics and experiment environment and talk about some related work and the conclusions drawn. There have been many efforts to address smart meters privacy issue. The fine-grained profiles of energy usage reported by smart meter threatens user privacies since adversaries may learn a lot about users' behavior pattern. The meter readings can also be used to analyze the type of appliances being used by detecting the load signatures. Battery-based load hiding couples the meter reading from actual usage profile by charging and discharging a battery at the premises of the end customer in a strategic manner. The design of how to control the battery is at the heart of a BLH system. The reinforcement learning BLH shapes the meter reading to rectangular pulses to hide high frequency usage pattern. The pulse magnitudes are mainly determined by the amount of energy remaining in a battery, thereby significantly reducing the correlation between the meter readings and the usage patterns in the low frequency shape. The decision policy for choosing a pulse magnitude also takes into the account the goal of maximizing savings in the energy cost by charging the battery when the price of the power is low. The reinforcement learning approach makes it resilient to changes in user behavior patterns since the algorithm keeps updating the optimal decision for a state in the runtime. The smart meter measures the energy consumed once in every fixed interval. The fixed interval is defined as the measurement interval. Usage profile is the amount of energy consumed by appliances in the nth measurement interval. The amount of energy drawn from the power grid in the nth measurement interval is referred to as a meter reading. In order to decouple the usage profile and the meter reading, we put a rechargeable battery at the end user and select the value of meter reading without considering the value of usage profile. The battery plays as a buffer between the usage profile and the meter readings. The battery level denotes the amount of energy remaining in a battery at the beginning of the nth measurement interval. Rn is used to denote the price per unit amount of energy in the nth measurement interval. Let's consider a simple example case to understand the strategy to obtain cost savings. If we consider there are two price zones in a day, one is the low price zone and the other is a high price zone. If we charge the battery in a low price zone and use the energy in the high price zone, we can achieve maximum cost savings. In general, the cost savings can be obtained when the original cost for what a user consumes is larger than the bill that the user pays to a utility company. The adversaries can identify what appliances is being used by detecting signatures in the usage profile. The low frequency shape of the usage profile can be used to identify the user's behavior patterns. The first design goal is to protect user privacy by hiding both the low and high frequency usage patterns. The second goal is to maximize the expected savings of a day. Previous work have indicated that changing the value of meter reading in every measurement interval may cause significant correlation between the usage profile and the meter reading. In order to account for this issue, the control algorithm discussed changes the value of meter reading once every ND measurement intervals, which makes the meter reading look like rectangular pulses. The pulse width for which the value of meter reading is held constant is referred to as a decision interval. AK is used to denote the magnitude of a pulse for the kth decision interval. For the mathematical equation of battery level shown in the slide, the magnitude of AK is based on the current battery level. So therefore we now have more randomness and uncertainty involved in determining the value of AK because the value of battery level is not known to the adversary. Therefore, from the adversary point of view, it is much harder to know how the pulse magnitude is selected. The value of meter reading staying constant for the kth decision interval is effectively similar to flattening high frequency variation in the meter readings. However, the approach discussed above will also hide the low frequency variation in the meter readings. The design of deciding the value of the pulse magnitude without considering the value of user profile for the decision interval is at the heart of the control algorithm. Deciding the value of pulse magnitude is defined as an action. A decision policy determines what action should be taken for each decision interval. The maximum cost savings of a day can be achieved by finding the optimum policy as defined in the presentation. It is important to note that the value of Sk will be negative when the battery charges and it will be positive when the battery discharges. To achieve maximum cost savings, we have to choose the value of A such that the overall sum of Sk over the time interval can be maximized. The optimal policy can be described by the recursive equations known as the Bellman equations. Pk is the probability that the change in the battery level for the kth decision interval is C. In the presentation, Q is defined as the optimal action value function and V is defined as the optimal value function. The optimal value function describes the optimal cost savings that can be achieved at the state assuming the following actions are all optimal until the end of the day. As we do not know the probability distribution of usage profile, we try to learn it by a sample mean using the form shown in the presentation. Here alpha represents the learning rate. For a sufficiently small value of alpha, Q can converge to Q prime. The battery level is a continuous variable, therefore the number of states is infinite. To account for this issue, we approximate Q with a function estimator that is a linear combination of representative features. Q can be approximated by the following form shown in the presentation. The features are combination of the normalized battery level and the normalized decision interval index. For each action A, we represent Q using 6 features. Q can be rewritten in the form shown in the slide. We notice that the Q update rule is to move to convergence by reducing the magnitude of del Qk. This slide discusses the two kinds of heuristic method to boost up the speed of learning. In reinforcement learning, convergence to the optimal policy takes time, which is exactly proportional to the time to collect enough number of training samples. So therefore we can reduce the wall clock time to convergence by feeding artificially generated data. There are many ways to generate synthetic data. By shifting the user profile in the time domain or by picking a random number based on the statistics of the user profile, we can generate synthetic data. The paper discusses the use of statistical approach to generate synthetic data. For each measurement interval n, we track the sample distribution of usage profile. For d days, we generate d days of artificially generated user profiles where xn is randomly sampled according to the statistical characteristics of the nth measurement interval. Another method to boost up the learning is through reuse of data. We can reuse the usage profile sequence by training the system multiple times using the same data. By using the usage profile sequence multiple times, we can fully utilize every data sample even in the early phase of learning. The inner loop of the algorithm corresponds to the core procedure that determines how to choose the pulse magnitude, the meter readings for the kth decision interval, and how to learn the optimal policy that maximizes the cost savings. The outer loop describes the iteration of the inner loop over days. The reuse mode means that we use the usage profile that is pre-collected at the day. The load signature can be easily detected by watching two successive values of the usage profile. So therefore it is important to determine how well we can hinder the adversary from guessing the length to sequence of the usage profile by observing the same length of sequence of the meter readings. We can quantify this metric using normalized mutual information as discussed in the presentation. In the given form, H denotes the uncertainty. So therefore the given form determines how much uncertainty about usage profile is reduced by observing the meter readings on average, normalized to the uncertainty of usage profile. The smaller value of Mi means the fewer information about usage profile leaked from meter readings. So therefore for our system we would like to have a smaller value of Mi. Pearson correlation coefficient between usage profile and meter readings is used to determine how well we can hide the low frequency shapes. The higher value of correlation coefficient, the more similar the low frequency shapes of the usage profile and the meter readings are. As a metric of cost savings, the saving ratio quantifies the expected ratio of the cost savings to the original cost for what the user actually consumes for a day. In this slide, reinforcement learning BLH is compared with the representative high-frequency flattening algorithm to compare the ability of the system to hide the low-frequency shape of usage profile. The figure shows the typical usage profile and the meter readings and corresponding battery level changes. In reinforcement learning BLH, the meter readings gives almost no idea of what the low frequency shape of the usage profile looks like. Rectangular pulses of varying magnitude show up randomly to charge and discharge the battery. In contrast, the low-pass scheme shows a clear correlation in the low-frequency shape between the usage profile and the meter readings. The adversary can figure out the correlation by looking at the bumps in the meter readings. This kind of information can also be used to figure out when the house is left empty and when the users come back home. In this slide, we compared the correlation coefficient, mutual information, and savings ratio for the low-pass scheme and reinforcement learning BLH system. We can observe from the figure below that reinforcement learning BLH is indeed better in hiding the low-frequency shape than the low-pass scheme by an order of magnitude in the correlation coefficient. The mutual information for reinforcement learning BLH is slightly higher than that of the low-pass scheme. The reinforcement learning BLH can achieve more cost savings by increasing the battery capacity. This slide shows how helpful the heuristics are to expedite the learning and to improve the cost savings. To decide the conversions time of reinforcement learning BLH, we define the error as the sum of del Q prime over a day. We can say that the algorithm is converged when the error starts to saturate below. We can see from figure in the presentation that without the heuristics, the conversions takes about 1500 days, which is not practical at all. Meanwhile, applying our heuristics, the algorithm converges within 10 days. Figure below shows that the reuse heuristic not only reduced the conversion time to within 10 days, but the savings ratio becomes the largest when all heuristics are used. Thus, we can think that our heuristics are effective in reducing the conversions time as well as improving the cost savings aspect. Figure below shows how reinforcement learning BLH acts when the decision interval varies. We can see from the figure that the savings ratio goes down when decision interval increases, since the larger decision interval means the fewer chances to drive the battery level in the direction that we want. The mutual information also moves in the reverse direction with decision interval. This is because the larger decision interval is more favorable to hide the high frequency variation, as the low pass scheme is slightly better than the reinforcement learning BLH. On the other hand, the correlation coefficient does not seem to change significantly according to decision interval. Thus, we can conclude that the decision interval plays a role as a knob to control the trade-off between privacy protection and cost savings. Figure below shows the performance metric variation according to the battery capacity. The cost saving is proportional to the amount of energy that is charged at the low price and used at the high price. Thus, the savings ratio increases when battery capacity goes up. We have observed that for a larger battery capacity, reinforcement learning BLH gets more chance to choose the pulse magnitude as the maximum possible value when decided to charge. We suspect that this is because the algorithm tries to charge more energy in the battery to achieve maximum cost savings and thus causes the pulse magnitude to have a less correlation with the usage profile. For this reason, the correlation coefficient shows the inverse relationship with battery capacity. The MI does not show any linear relationship with battery capacity. Therefore, we can conclude that the larger value of battery capacity is more favorable to reinforcement learning BLH for both privacy protection and cost savings. One of the advantages of reinforcement learning BLH is that it can handle the change in user behavior patterns smoothly, since it keeps updating the weights at every time instance. The decisions will become more suboptimal if the underlying data differs from future data. However, this issue is common for all MDP approaches due to its inherent difficulty in obtaining the true underlying distribution based on limited data. Reinforcement learning BLH keeps updating the weights as new data becomes available to alleviate this issue and hence can be useful even if the user behavior pattern changes. If there is a day when energy usage is usually low and deviating from a daily pattern, the cost savings could go negative in that day. This is because the charge energy at the battery is not fully used at the high price periods. However, in such a case, the following day can use the energy saved at the battery without charging it again, thereby resulting in higher cost savings than that of a typical day. The savings ratio that we have shown in experiments is an average over days, taking such a case into account. In our experimental environment, we have shown that a battery of 5 kilowatt hour can achieve $7.5 of cost savings from $50 bill per month. Research conducted has studied a new battery-based load hiding algorithm that not only addresses the limitations of the existing solutions but also achieves the optimal savings in the energy cost. Reinforcement learning BLH hides both the low frequency and high frequency usage patterns by shaping the meter readings to rectangular pulses of varying magnitude. Energy expenditure is reduced in the optimum way that charge a battery when the price of energy is low and uses the stored energy in the battery when the price is high. We have approximated the optimum action value function by a linear combination of a few selected features so that the real usage value can be taken into account without quantization and computational complexity is significantly reduced. The learning time of reinforcement learning BLH is significantly shortened by generating synthetic data on the fly and reusing original data at the beginning of learning. For future work, the research can be extended to integrate renewable energy sources into the picture where we may produce profit by selling energy in the battery. Another interesting direction is to further reduce the convergence time of reinforcement learning by enhancing the way of generating synthetic data in the runtime.